what I want to do today, because it's the first talk in the series, is to focus on the big picture. You know, when you read some paper or you go to a conference, come into some talk, you see a lot of like complicated stuff. But what happens is every paper, usually it just modifies one little thing. So once you figure out what it modifies, everything's clear. But what I want to do is, instead of like diving deeply into a specific thing, I'll talk about you know, the big picture, and I'll dive into one specific thing on Laplace transforms towards the end. But what is the big picture? I think it's important, if you're doing theory, like every few weeks, ask yourself, you're researching something, why are you researching it? Because like in math, it's very easy to get caught up in these lines of research, and often they don't go anywhere. And you know, you may be proving some obscure property, and other pure mathematicians love it, but if you want to be cared by many people, you kind of want to be able to connect your research to practical tasks. So what is the big picture? Well, the big picture is a lot of the tasks you're dealing with in machine learning, you essentially have a data set. So you start with a data set, then you have some inputs and outputs, and you want to find the function which maps, given this input, it gives the correct output. So for instance, you may have like input is a picture of a cat, and the function should output label cat, or it should be a picture of a cow, and the output should be a picture of a cow. This is actually a surprisingly flexible paradigm, because with GPT-4, the actual function they tried to learn is a function which takes your input, could be like a picture is worth 1,000, and the output is words. So basically GPT-4 is trained to do the next word prediction. And what was kind of like magically surprising is that you learn a function which predicts the next word, and somehow you end up with a function which you can say like what's 17 plus 32 equals, and this, it just outputs the number like 49, even though it may have never seen like either 17 or 32 in its training set. So this was kind of surprising that this works. So it's one of those emergent capabilities. But the bottom line is, the underlying objective, you have this pairs of inputs and outputs, and you want to learn a function which maps them. So this is your master task. You want to learn this function. And how do you do this? So there's many ways. There's, you know, people experiment with genetic algorithms. It was a big thing in the 90s. You can do like decision trees, also a big thing in the 90s. You can do kernel method, was super big thing in the early 2000s. So nearest neighbor algorithm is an example of a kernel method, and it's still used. But what we will talk about here is the fourth option, which is neural networks, or sometimes you call them differentiable programming. And what this is you're finding this function, but you're assuming that you're able to take derivatives. So you have some function form, and you have like an extra tool. You can take derivatives, which helps you find this function. So let me dive deeper into what neural networks look like. So you may have an architecture. You have this X comes in the bottom, and then it goes through some layer, like linear layer, and then here maybe there is like an activation. Oh, okay, I can draw, but anyway, so there may be some nonlinearities in between, but you're multiplying this input at each layer, transforming it, and then you get some output. And in this form, if your W's are matrices, you can use derivatives. So more concretely, you can think of these three matrices, you stack them together, and you want to learn these three matrices, and we can basically call all these three matrices as just you know, just your parameter W. Right. So the task here is to find a function where it gives the correct output for each input, and the way you treated in differential programming, you can basically stack. You have an output for each input, and then you can stack all of these things into a matrix like this. And you just say, we just have a single function. So you can get rid of, you can kind of like bake in your data set into your function call. So your function f basically takes your parameter vectors and it outputs all the labels. So it's like a batch prediction function. So that's your underlying task. You have some function which produces a batch of labels, and you're trying to learn W so that the thing you're predicting matches the thing you want to predict. So there's a trick in calculus called Taylor expansion. So if you have a function of W can be a vector, you can expand it using derivatives. So basically, like in one dimension, you can think of, you have some kind of a function. You first approximate it with a linear function, and then you approximate it, constant, and then you approximate it with, let's see, with a linear, and then the next stage you approximate it with a quadratic. Let's see, with a quadratic like this. So this is a standard thing you learn in calculus, but what's important is if you take this expansion out to infinity, it's identical to the original problem. So you can have your function of W, where W is parameter vector, either in the original form, or you can in this expanded form in terms of derivatives. So the original task, what we have is we're trying to find W are weights such that the outputs are equal to what we want. And you see in this expansion, the W is right here. So this is our W, and then you see it here, and then you see it here. Let me just delete this. Okay, so yeah, so basically there is just a single variable in this expansion. So that's the original task. This is just an algebraic reformulation, but the simplified task is, okay, all these extra terms, let me simplify this function, and I just simplify it by removing all of these terms here. I just get rid of them. So the simplified task is you want to find a simpler function, or you want to find a function from the simpler family, which produces the labels you want. And it should be clear that this task is sort of a simpler task than before. So we can use it as a proxy for the original task. So what kind of questions do we care about in the original task? Well, we're trying to fit the neural network, and we may be interested in how hard is it to fit this neural network. And the original question is too hard, but you simplify this, you can actually answer a question for the simplified problem, which gives you a lower bound on the difficulty. So if solving this problem takes you like 5 days, then the original problem is going to take at least 5 days. Does it make sense so far?
Yaroslav, I've got a quick question.
Yep.
So since we're approximating only to the order of 1 here, so we know that it won't be the best approximation. So we've kind of introduced bias already. Is that the correct way to think?
Yes. So basically, the reason for this approximation is I want to get a sense. So the issue is not to actually learn the function. The issue is to answer the question, how hard is it to learn this function?
Understood. So the lower bound on that.
All right.
Okay, cool. Thank you.
Right. So basically and this is a very common technique, like in physics, what happens in this nonlinear models, we almost never are able to do any kind of analysis on nonlinear models. And they just say, well, pretend it's linear, and then you answer some questions on this linear version, and then hope that the answers are still valid in the original setting. And what we've been finding in very large neural networks, we're actually finding that when they're very large, they're actually very similar to linear. So all this work in neural tangent kernel, for instance, they are basically assuming our prediction function is linear. And a lot of work in gradient descent, they're assuming it evolves as a linear system and getting something that's close to what's observed. Okay, so once we simplify this thing, you can rearrange some things, and the takeaway is that to answer the question is how hard is it to solve the simple problem is the same as to answer the question how hard is it to solve this problem AW equals B. So A is a matrix, B is a vector, W is a vector. So the takeaway here is to answer how hard is it to, fit the simplified like linear neural network. It's the same as to answer how hard is it to solve some system of equations. And this is system of equation in matrix form. In original form, it would be like something like 1x1. Actually, I'm using W as the variable. So plus 5W2 equals 3. And then maybe it's like 4W1 plus 9W2 equals 9. So you have the system of equations. And these values 1, 5, 4, 9. That's your A matrix. And then 3, 9. That's your B vector. So you're given this matrix and a vector, and you're saying, how hard is it to solve the system? And what I'm saying is that in order to understand how hard it is to fit a neural network, it is necessary to understand how to solve a corresponding linear system. And this is essentially most of the analysis and results in gradient descent. They end up doing some kind of linear approximation and answering this much simpler question. There's actually two ways of viewing the linear equation solvers. You can call it, it can be an estimation problem. So this view is estimation. But there's an equivalent view called optimization. So in optimization, you're saying instead of finding W such that this is correct, we're trying to find W such that the difference between the two sides is the smallest. And when this equation is solvable, the two approaches give the same answer. So you can basically take this minimization problem. Let's see. Delete this thing. So you can take this minimization problem and you can expand it. So essentially, solving this estimation problem, it basically comes down to quadratic minimization. So it's the same as minimizing this function 1/2 W transpose HW, where H is this is basically a matrix squared. And final simplification. So now to minimize this problem and to solve this linear equations, there's many different methods. So gradient descent is just one of the methods. So we can, and it sort of also gives a lower bound. If we can solve something, in 20 steps using gradient descent, then other methods, then the best possible method will take at most 20 steps. So now we specialize even further, and we say, well, how hard is it to solve this problem with gradient descent? Because it gives information to the original question. And gradient descent, one thing to notice with gradient descent is that it doesn't care about the rotations of the problem. So for instance, if you have like a problem like this, if you initialize randomly equal in all direction, we can rotate this thing, and the gradient descent on average it will take the same amount of time, no matter what the rotation is. And what from linear algebra is that whenever you have a quadratic form like this, so this is our quadratic form, you can always rotate it to make it diagonal. So if H is some matrix which is not diagonal, we can always there's some matrix 1/2 U d U, which is essentially has the same shape, but it's rotated, and U is a different coordinate system. And when it's diagonal, you can write the objective in this new coordinate system as basically a quadratic in d dimensions. You have this quadratic with d terms. So what we have here is that in order to understand how hard it is to solve this problem, we can, it's necessary to understand how hard it is to minimize a function which is just a simple quadratic with d terms. Any questions? Make sense so far? Okay, so the goal of this was to motivate, like, why do we care about minimizing a simple quadratic? Well, the reason we care is because ultimately we want to know how hard is it for a neural network to fit things, because if we can measure how hard it is, we can improve it. And as a proxy for this, using the steps, we know that it's necessary to understand how hard it is to minimize a simple quadratic, like x squared plus 1/2 y squared. So this solving this problem gives information for the original task. This NTK, there's a lot of NTK literature. It kind of hides the fact that neural tangent kernel is basically the way it comes up is you approximate your neural network as a linear function, and the neural tangent kernel, it's we have this Hessian, the quadratic is this a prime a, but the NTK kernel is a prime. The reason for the difference is because the shapes are different. So if A has a lot of columns, this H matrix is very big, but this A matrix is normal size. So sometimes it's worth looking at this matrix instead. But what's important is that these two matrices have the same non-zero eigenvalues. So what this means is that minimizing the function like a w, and then minimizing a function u a, these two converge at the same rate. So this is a non-trivial fact from linear algebra, but it's true. So whenever you see NTK, most of the time you can just say, well, let's just pretend it's a Hessian. It's not exactly true, but it's true in the sense that the rates of convergence are the same. So the reason I bring this up, some people were talking about neural tangent kernel, and there's now tools where you can take a neural network and you can ask what are the NTK eigenvalues. And this NTK eigenvalues, you basically can get these eigenvalues. You can form this function with the eigenvalues. So for instance, you run your JAX package, which says NTK eigenvalues are like 1, 2, 5. The question you care about is how hard it is to minimize a function 1 times W1 squared plus 2 times W2 squared plus 5 times W3 squared. So difficulty of minimizing this function also relates to difficulty of fitting that original neural network. Great. Any questions so far?
I think there was one in the chat.
No, I think it got answered already. Thank you.
Okay. Okay. All right. So this was all about the big picture, why we care about minimizing quadratics. And now I can talk about, this tool called the generating functions, which is pretty useful for doing this analysis. So basically, you have some function and you want to minimize the gradient descent, and you want to understand what does the trajectory look like. So here's an example trajectory. I have like this. This is my function here. Let me zoom in. So I start with some point, and then I perform gradient descent. And here in the talk, you see I never have step size in my formulas because I always set step size to be 1. So whenever you think about step size, it's 1. So you have some quadratic here, and then you're minimizing using gradient descent, and you have this trajectory. So you start with this point here, do 1 step, you go to this point here, and then you do 1 step, and you get to this point here. And you want to have some tools to, given these coefficients, you want to, get this trajectory. Right. So basically, generating functions give you a way to map between different representations of your problem. So in this problem, we have a quadratic. I like to think of there being 3 different representations. One is the representation of coefficients or eigenvalues. And I call them eigenvalues because this function j, you can write it as in the matrix form of like x, y times x, y. And these values 1/2 and 1/3, they're the eigenvalues of this matrix. So we have this coefficient or eigenvalue domain. Next domain we care about is the time domain. So the time domain gives the points observed during optimization. So it's your gradient descent trajectory. And the final thing, which I will talk more about, is this frequency domain. So frequency domain is the thing which makes some magical things possible. So what is this frequency domain? So frequency domain basically comes when you take this trajectory and you summarize it in several different ways. So how can you summarize? So this is your time domain, your list of points observed during gradient descent. Well, one summary, you can just add up all the points. So you're doing a weighted sum where all the weights are 1. So you add them up, and you get this point here. That's your first point of the frequency domain. And then another way of summarizing it, you use exponentially decaying weights. So you weigh the first point by 1, you weigh the second point by 1/2, third point by 1/4, and then you add them up, and you get the second point. And then the third point, your exponential decaying weights are 1/3. So first point weighted by 1, second point weighted by 1/3, third point weighted by 1/9, and then you add them up and you get this value. So these are the calculations. If you do this, you get a different representation of the trajectory. It's called the frequency domain representation. Does it make sense so far? All right, makes sense. And why do you do this? Well, basically what happens, there's sometimes things are easy to do in time domain, and sometimes they're easy in frequency domain. So there are cases when you can actually obtain, you have a formula for this trajectory in frequency domain that you can obtain, but you don't have the one for time domain. So you do this. So this is actually very similar if you've heard of people doing Fourier transforms. There is this saying in Fourier domain, convolution becomes multiplication. So it's actually the same thing. So Fourier transform, it takes this time domain and then it transforms it using weighted masks, and it makes some operations harder and some operations easier. So it's a tool you do to expand your range of options. Okay, makes sense so far? Okay, so now I will give this grand map of generating functions and how they occur. So we have this objective here. So 1/2 x squared plus 1/3 y squared. You can take the matrix representation. So you can write this in the matrix form. And we call this matrix H. So we can write our objective in this way. And then when we look at what happens after we apply our gradient descent. Basically, we'll go into more details later, but the value of the position of your estimate after t steps, it's basically this formula. And this is your trajectory in time domain. And what happens actually in higher dimensions, you can approximate this thing with an exponential. So yeah. So I will, so in parallel, you can either look at the original representation or you can use this transformed representation. And then if you apply the Laplace transform to this thing, you get, well, in the first case, the thing you get is called the generating function. And the second thing is sometimes called the resolvent. And if you've done discrete math, you cover generating functions there. So generating function is something that describes a sequence. So in this case, it's the generating function of the sequence of matrix powers. So this is the matrix in question. It's the matrix which describes how the gradient descent trajectory evolves. And the sequence, you get the sequence by taking this matrix to different powers. So this thing maps you to frequency domain, and there's actually an alternative representation of this quadratic form. Is instead of listing these coefficients in the matrix, you can look at it as a probability distribution. So think about a number line of all possible versions of coefficients, and then whenever a coefficient occurs in your form, you just have this this point mass here. So there's some probability of having this coefficient at 1/2, and then there's some probability of having it 1/3, and the rest of the things are 0. And what happens when you have this form, and you can write it in terms of Kronecker delta functions, what happens is you can take a Laplace transform of this probability density, and what it will give you will be your expected error after t steps of gradient descent. And alternative way of getting this, you can start with your quadratic form. You obtain your trajectory here, you approximate it with an exponential, which is pretty close, and then you take the trace of this matrix. It also gives you this expected error at time t. And then there's another transform called Stilch's transform. So you can take this expected error at time t, you do another Laplace transform, you get this frequency domain representation of the error. So notice earlier we talked about frequency domain of the trajectory, but if you take the average value of all the coordinates, that gives you the error, and that gives you this trajectory. This is a scalar and this is a vector, and that's how you map between them. So yeah, so this is a lot to take in, but I'm just giving it, throwing it out there just to give you some taste of how things are connected. So everything is connected, and this can take several lectures to talk about all the different paths you can take, but the two paths I will mention here, the path I will talk about in the next section will be how to get the path here. So laser. So you have this quadratic form, and then you want to get this expected error at time t. So you can either take this path or you can take this path here using Laplace transform. And you notice in the description of the talk, it mentioned something about that paper from Velikanov. I actually won't talk about this. It's a bit more advanced, but the path that they take here is sort of this path. So what they do is they come here and they do some operations here, and then after they figure out what the trajectory looks here, they do the reverse step. So you can actually go from the frequency domain representation to a original time domain. This thing can be either like inverse Laplace transform, or there's another thing called Covariant theorems. But these are different ways of going from frequency representation to time representations. So maybe I can talk about it in the next lecture. Yeah, so any questions so far? I guess it's a lot of questions, but I will go into more details on a specific path on this graph. All right, so as promised, this is like the overall map, and what I will talk about, how we can get, given this quadratic form, how we can take this path and actually get a formula for the error after performing these steps of gradient descent. So here's a simple example. We have a one-dimensional objective. So W is our variable, H is our Hessian, and we're performing gradient descent. So if you do basic calculus, the gradient is just H times W. This is actually the reason for this 1/2 here. If you have this 1/2, the gradient is very simple. And when we subtract the gradient, we have W is W minus HW. So you see at each step of gradient descent, your weight is multiplied by a factor of 1 minus H. So after t steps of gradient descent, it's like 1 minus H to the tth power multiplied by the original starting point. Make sense? But what happens if it's multidimensional? So you have this function of d variables, and they're the same. Well, if you do the algebra, you'll see that it's the same. So ith coordinate of W is just this ith coordinate is just multiplied by this factor t times for step t. And what we care about is error. So error is like if we have our solution, in this case, our solution is 0. We're minimizing it, and then we have our current thing here. So error is just the difference, the distance. Oh, it's the vector between the solution and the current value. And what we care about is the norm of the error, which is like the squared norm of this weight vector. So we have the formula for this weight vector, and then we can find the formula for its norm. So it's basically a sum. And there's another trick you can do. Well, like one annoying thing here is in this formula for error after t steps, you have this W0. And in optimization literature, and like what is W1? Or yeah, what is W0? It's like annoying, like get rid of it. So optimization literature, what they often do is they take W0 to be the worst possible. So they're very pessimistic. And what happens actually in high dimensional regime, worst possible case is actually very bad. So if you look at optimization papers, you see people talk about condition number, and if your Hessian has like flat in some direction, things become like very bad. But in practice, you can have like completely flat objective in some direction, and you can still optimize it. And the reason you can is because in real life, you almost never hit upon the worst case. Like in the worst case, you're like completely stuck, but in average case, you're fine. So for this reason, like when I read optimization papers, I see a term, some like condition number. I'm like, okay, this is not going to be useful to me. But what do we do if we don't want to, take the worst case because it's very pessimistic? Well, we can just assume W0 is random, and we can look at the expected value. And you can show, and I can give a link. It's non-trivial to show this, but the result is actually very simple. If W0 is assumed to be random on a circle of some radius, let's say it's radius 1 without loss of generality, and it's like uniformly distributed. So if it's random in this way, then your average value is just an average value of the sum. So you know you have the sum with d terms. So we have like d here. So d. Yeah. So to get the average norm after t steps, adjust the average term of the sum. So this is an alternative way. How do you get rid of w? And it's better, in my opinion, than the standard approach because it's not pessimistic. It's average case. Any questions so far? Oh, VA4AZ has a question.
So I think this might be a trivial question, but what I'm trying to understand is, so they're giving this Laplace formulation. Does it make it computationally more feasible? Like I understand like it's another way of looking at it, but does it help on the compute side if you're
Yes.
it?
Yes, it indeed the reason you do Laplace transform is because it helps on the compute side. And let's see, how can I explain why it helps? So it helps on the compute side. So what happens? So one example of the Laplace transform is you have a sequence. So for instance, you have a sequence matrix like A0, A1, A2, and you have another sequence B0, B1, B2. But what you care about is the sequence A plus B to the 0, A plus B to the 1, etc. So suppose you have a special case, and this is what happens in this Velikanov paper. Suppose A is a diagonal matrix. And in my example, what we talked about, our gradient descent is always diagonal. But in that paper, they actually look at SGD, and in SGD, it actually becomes a diagonal plus rank 1. So your B matrix is like this rank 1 matrix. It's like U times U transpose. So what happens is, it's easy to take powers of diagonal matrices. It's easy to take powers of rank 1 matrices, but we don't have an easy way to take a power of diagonal plus rank 1 matrix. However, it's easy to find the generating function, like this thing is easy, G of A. This thing is easy. And combining them, this thing is also computationally easy too. So what happens is, in the Laplace transform space, this kind of operation becomes easy. So we have this easy to compute formula for the combined version. The difficulty is there is no free lunch. So the difficulty, you can't actually invert this directly and get the formula for, for the sequence, but there's tricks. There's tricks. You can get like asymptotic formulas, numeric formulas. So it's like an algebraic trick. Algebra is easy to do in the Laplace transform space, and then you can do numeric approaches to go back. So to answer your question, yes, you do Laplace transform because something is easy after doing Laplace transform.
Thanks.
Okay, so to go back, so what did we care about? So I wanted to show how Laplace transform comes up in analyzing how loss changes as a function of time. So here we obtained the formula of the norm after t steps. Here we do this random trick to get rid of W0. So now we do a second trick. The second trick, we replace this this difference with exponentiation. And if you forget where this equality comes from, it's essentially E minus X is equal to 1 minus X plus some other stuff. So stuff on the order of X squared. So if X is small, then, this thing approximately holds. So let's see. It's the approximate sign. So this is something that's approximately true, but what we will see in the next slide is that if you do this approximation, you actually don't lose very much in high-dimensional regimes. So you can just replace this power with exponent. And the final trick you do is you phrase this as an expectation. So if you've taken probability, maybe you are familiar with this concept of taking an empirical mean. So you have some like k data points, and there's an empirical distribution. So in this case, suppose I have just 2 data points, and I want to find the expected value of some variable. So there's 2 data points, so there's like 2 point masses on this 1/2 and 1/3, and then we can take expected value of this this quantity in the middle. So it's basically just another way of expressing the sum. Does make sense so far? Right, but now if you've taken probability, you may know that this thing looks familiar. This expected value of e to the something. There's this thing called the moment generating function. So if you have a random variable x, this value here is known as the moment generating function of x. And it is also known as the Laplace transform of the probability density of x. So in our case, you recall that we started with, j equals 1/2 x squared plus 1/3 y squared. So our probability density is this thing. So we have a point mass at 1/2, and we have a point mass at 1/3. And basically what we showed here is you can take Laplace transform of this, you take care, you have like this factor of 2. But the end result is that once you take the Laplace transform of this probability density, this gives you a way to compute this quantity, which is the expected distance to your target location. Does it make sense so far?
I have one quick, this might be a dumb question. Here
Dumb questions.
Here x is the random variable, or is it the p of x is the random variable that's going into the
Right, so p is the probability, x is the random variable, but here I call the random variable h actually. So let's see. So the random variable is h. So what you're doing here is h are my coefficients. So I'm summing over all possible h of i's. So h's are my random variables. And here I'm saying that there's 2 coefficients. There's just 2 possible values of h. It can be like 1/2.
So the coefficient domain, basically.
Yeah. So h is my coefficient, and I have some probability of having this coefficient 1/2 and coefficient 1/3. So this coefficient is this random variable. So here. So this is basically 2 tricks that you have to be aware. So first, you can replace this powers with exponents, and 2, you can replace write this sum over some values as this empirical expectation. And once you have this in this form, it's like, oh, this is just the moment generating function, and the moment generating function is Laplace transform. Right, makes sense. Cool. So one thing you may wonder about, I kind of just replaced this this power with exponent. Like, is it good? Sometimes people do use this approximation, and they call it the continuous version of gradient descent, and they say you must take a very small step size. So in the limit of tiny step size, this approximation is valid. But it's actually valid even for large step sizes. So here's an example, like over time. So one graph is this exponent version, other is the powers, and you can see that when things are decaying, eventually they both converge to 0, so they become close in absolute value. But what we care about is, so here what I did, I performed the gradient descent, and in one case I used the original version where I take powers, and in the second case I did this exponential approximation. So in 4 dimensions, you can see there's kind of a big mismatch. But if I do 1,000 dimensions, and this is for a function where it's like where they're decaying exponential. So this is like y squared plus, oops, let me remove this thing. So this is for a function y squared plus 1/2 y2 squared plus 1/3 y3 squared. So essentially, I take this function and I minimize it with step size 1, which is a fairly large step size, given that using step size 2, gradient descent will diverge. So I'm using this large step size, applying this approximation, which traditionally people use for this continuous limit, but it actually gives a very close match, even for large step size. And I have a link here. You can, this is like Wolfram language notebook, but you can see the code used to generate it. Yeah, and this is just a more sanity check. This is an example. This is even in 17 dimensions. So this is gradient descent of this function, like here, with just 17 dimensions. And these points here are, this points here is what the true observed value is, and this red curve is what you do when you apply Laplace transform. So it's an upper bound, but it gives a close match, even if dimensions are not very high. Yeah, here's a link. You can, if you know mathematically, you can take this code and you can play around with it yourself. Yeah, so this is all I wanted to tell you today. Do you have any questions? Nobody has any questions. Oh, go for it.
Well, so what is TLDR? Like what is it that we showed at the end?
Yeah, TLDR is that sometimes, so TLDR, what's it? So one TLDR is you should remember that Laplace transform exists. The second TLDR is if you have okay, here's a good TLDR. So so if you have gradient descent, you know, it minimizes the function. One TLDR is that if you're interested how this is like error at MT. If you're interested to know what is average error when T is very large, so when T is very large, the error is approximately e to the smallest eigenvalue mean of T. So this is if you look at optimization papers, there are always this condition number which has the smallest eigenvalue. So this is the infinite width limit. If you care about, you know, in this regime, you can take, you know, Taylor expansion of your thing, and it's actually becomes approximate to, you know, it's proportional to the trace of this trace of your, it's basically the sum of your coefficients. So it's proportional to the sum of your coefficients times T plus something. And the question is, what happens in this intermediate regime? How do you find it? And the answer is use the Laplace transform. So if you have a formula for what your coefficients are, so for instance, if your ith coefficient is, you know, 1, let's see, 1 over I. So if you have a formula like this, you can take Laplace transform on a formula, and then you get the actual formula for what this curve looks like. So like the thing here, I plugged it into Mathematica called the integrate function, and it gave me like an actual formula for the loss curve. And it's pretty close in 17 dimensions. In like 1,000 dimensions, it like almost exactly predicts what the gradient descent looks like. So TLDR, Laplace transform, tells you how, you know, gradient descent evolves, gives you nice formulas.
So you're doing the gradient descent on a linearized version. right?
Correct. Yeah.
And so can you comment on how this transfers over to like more realistic neural networks? And related to that, you sort of said that we should only pay attention to the average case in high dimensions. But like in real architectures, aren't vanishing and exploding gradients kind of a thing that because I guess like that condition numbers are related to that. So like, can you actually gloss over that?
Right. So first question is how it relates to the real neural network training. So the way it relates to it gives a lower bound on the difficulty. So essentially you can look at the problem, and from this you can say it's going to take me at least 5 days to solve the linear problem. It means for the actual neural network it will take you more than 5 days. So it gives a lower bound. And the second question, average case. So there is an issue, like the reason you take average case is because worst case is too pessimistic. So in high dimensions, like what happens if you optimize, for instance, a function is like this, and then in the end, maybe it's like 1 over like I don't know what kind of networks we have, 1 over a trillion parameters. So y 10 to the trillion squared. So the worst case scenario is your y 0 is going to be, it's all going to be zeros. And then it's going to be 1 at the last coordinate. And the worst case is a trillion times worse than the best case, because the best case is going to be when your starting vector is just you have 1 in the first position and the rest are zeros. So the discrepancy is, it's 10 to the 12th. And optimization literature often looks at the worst case, but what you see in practice, if you start randomly, you start from different positions, your loss functions sort of look the same. And it's true not just for linear problems, for neural network training. Things, you're in situations where things break or diverge, but once you tune things where things don't break, retraining with the same hyperparameters, it will give you approximately the same loss. So, we don't do this local seed optimization anymore. Your losses, they're all like looking like this, which tells me that, average case is the case you care about. Like in high dimensions, things concentrate around the average case. Whereas like the worst case is, you may be doing like this, but you actually never see the worst case.
I think to Leo's point, I think you mentioned that, you as soon as you look at the condition number, you don't even, you kind of ignore it. It might be better to Leo's point, to look at it from like, maybe do analysis of like different condition number, right? And see how far this holds true, because there could be some iterative methods that might actually still be like better, to solve for, given the real world scenario. Although, yeah, like having this analytical formulation is like great. But yeah, just adding to Leo's point.
Right. So, and I would say condition number doesn't matter, because in real world problems, condition number is indistinguishable from infinity. So if you actually look at the Hessian of real networks, like in the end, you have a tail of things which are like 0 and floating point 32, which means the smallest eigenvalues, they're not actually 0, they're probably very, very small, but you can't see how small they are in float 32 precision. Maybe you need like 1,000,000 bits of precision to get the actual value. And the reality is, it doesn't matter. It doesn't matter if they're 0 or almost 0, but from condition analysis, it actually matters a lot. Like infinite condition number and like a very large condition number, that's a factor of infinity difference.
Right. Thank you for sharing.
Yeah.
I think I have one question, like just probably not related to this one. Why is this analysis not more common in like?
I think so. So I have a theory why it happens like this. So what happens, there was a discussion on Twitter, what happened in like 1980s, people noticed. So in 1980s, you would minimize, simple things like the Rosenbrock function, if you've heard of it, but it's just like this weird function in just 2 dimensions. And people noticed in 2 dimensions, if you look at what happens when t goes to infinity, like if you look at this worst case convergence rate, it actually matches the realistic, the actual observed convergence rate. So in 2 dimensions, your worst case is your typical case. So people got really into this, condition number-based analysis, but in the last 40 years, your dimensionality actually increased a lot. So it went from 2 to, 10 to the 12th. And what happens is that in high dimensions, this analysis no longer works. So what happens when you're optimizing, eventually your gradient descent at the very end, it will be optimizing the worst dimension. So like in this case, you have like this function. If you really want to get like perfect result, eventually you'll be bottlenecked by this. But the number of steps you need to get to that point is around d squared. So imagine if you're doing 2-dimensional optimization, after something like 4 steps, you're already in the worst case scenario. So worst case is actually a very useful thing to look at. When you're looking at, this case, you need to look at, steps equals d squared equals 10 to the 24. So for this high dimensional problem, this worst case is actually never observed. But people in optimization literature, they never kind of updated their priors. They just continue on this path, convergence theorems. Let's prove more convergence theorems. But yeah, I think it's just inertia. It's like culture, inertia. There's kind of a gap. Yeah.
It could be one more thing, right? Like I think a lot of people who are coming from the control system side or linear dynamical systems, they haven't looked at these problems as much probably to give that formulation, from a culture perspective. Like it came from a CS side, so they just never knew how to look at these problems from a Laplace and transform perspective.
Laplace is used extensively in control. Actually.
Yeah. Actually, I majored in computer science, and they never taught us Laplace transforms. I had to learn it myself playing around in Mathematica. So I think people look at these integrals, like I can plug into Mathematica, and there's a thing called exponential integral that it gives me, like gamma functions. I think people just are not exposed to these things, and they avoid them.
Right.
Yeah, I think because there was like a very recent paper that I read that was still discussing how I think even for logistic regression on separable data, like there's a huge gap between what theory predicts, and they had to exactly talk about the unbounded nature of the cross entropy, etc. And yeah, that's where I started getting this idea. So yeah, that was
yeah. Hello, Hrant. Are you dialing in from Armenia?
Yeah. Hey, thank you for the presentation. I joined late, but understood some of the things. I wanted to ask, why do you use Mathematica? Like,
I use
your like daily tool?
Yeah, so I use Mathematica because of the visualization API. So basically, it hasn't changed in the last 30 years. So I have made some visualization 30 years ago, I can still run it. And like open source, every 3 years, there's a new way to do a 3D plot. So it's kind of annoying. But I think with ChatGPT, so I I know people like Python, and I have some collab notebooks. I just never learned matplotlib, but actually ChatGPT is pretty useful. So it's actually going to make it much easier to me to map these graphs into Column.
Yeah, someone has to integrate ChatGPT into Jupyter notebooks, and
I think there's like thousands of people working on integrating ChatGPT into everything. They integrated it into Mathematica already, and it's been like a couple of months.
good. Okay, thank you.
Yeah, like first of all, I want to say thank you so much for the kind of presentation, even on the chat. Basically, it has been a really great lecture, and I think this is a very cool idea about generating functions and trying to like analyze this, it's a very different perspective.